Empiricism is the philosophical theory that all knowledge is based on experience derived from the senses. As a fundamental part of the scientific method, it means that all hypotheses and theories must be tested against observations of the natural world rather than resting on a priori reasoning or induction. Modern biochemistry, as observed, involves taking one clear, colourless liquid and mixing it with a second, different, clear, colourless liquid to create a third unique, clear, colourless liquid. Active voice. We performed the experiment. Passive voice. The experiment was performed. Active voice. We visited the laboratory. Passive voice. A laboratory was visited. Active voice. We looked for a way to show the invisible. Passive voice. The passive voice emphasizes the person or object receiving the action. For example, samples were analyzed. The active voice, in contrast, emphasizes the person or object performing the action. For example, we analyzed the samples. The passive voice is the voice of science. You hear it most often in the methodology sections of scientific papers. This is a good thing, particularly when you want things to be clear and easily repeatable. That's an important part of science, that things are able to be repeated. This repetition allows other researchers to test the validity of each other's findings. The passive voice allows us to focus only on the essential information needed to repeat an experiment. It doesn't often matter what the experimenter is called or what they had for breakfast. It doesn't often matter what they are wearing under their lab coat. These things are not variables or constants in the experiment. They are inconsequential. However, there is a movement away from using the passive voice, particularly in discussions around science. The passive voice can be a little awkward, requiring frequent uses of linguistic gymnastics to place the object receiving the action first. There could be another reason too. Whilst facts remain independent of our presence, the discovery of them and the application of these discoveries is a human endeavour. The way in which we go about learning about our world can tell us more about ourselves. In the active voice, we become responsible. Passive voice. A discovery was made. Active voice. We made a discovery, for better and for worse. Passive voice. Mistakes were made. Active voice. We've made a mistake. In The Republic, his treatise on justice and the city-state, Plato says, "The artist knows little or nothing about the subject he represents, and the art of representation is something that has no serious value." He felt that art, in general, takes us away from the truth, that it distorts reality, and as such, relieves us of any true insight. How can art and science collaborate when they appear to have an opposing relationship with reality? The Harvard philosopher Catherine Elgin, some 2,500 years later, argues that it is a necessary part of science that it departs from the literal truth when it comes to representation of concepts. Ideal gases, electron shells, rational agents. Without these distortions and simplifications, science is too complicated to communicate effectively. Nelson Goodman, a colleague of Catherine Elgin's, published a book in 1968. It's called Languages of Art, An Approach to a Theory of Symbols. The first section of this book is spent making the case that it is absurd to suggest that something must resemble a thing in order to represent it. Instead, he claims that representation should be seen as a particular type of arbitrary denotation, A thing represents another thing because we will it to. He says the arts must be taken no less seriously than science as modes of discovery, creation, and enlargement of knowledge in the broad sense of advancement and understanding. What he isn't saying, however, is that the practice of science can be replaced with the practice of art. Representation is only a fraction of the scientific process, and whilst it may share similarities with representation in art, there are also fundamental differences in approach. DNA, human suffering, time, covalent bonds, the atom, relativity, nationality, love, economics, temperature, light, architecture, disability, plans, reactions, borders, countries, sexuality, genetics, illness, life, death, employment, education, research. Irene Manton was a cytologist and botanist. She was the first female professor at the University of Leeds. She made fundamental discoveries concerning cell structure using microscopy. She looked at small things and saw the bigger picture. There is a building named after her at the University of Leeds. It is currently a computer department. There is a crater named after her on Venus. It is still a crater. There is a room named after her at Lancaster University. It is called the MANTON Room. It houses part of an art collection, her art collection. Irene Manton, scientist and art collector, was particularly fond of modern art. Japanese prints by Hokusai, paintings by Lowry, Hayter, Cézanne, Picasso and Braque. Irene would often hang works of art next to enlarged prints of cellular microscopy studies. Some people mistook the artwork for her actual work and wondered why she had coloured them in. She frequently drew lines of comparison between art and science. When talking about her love of East Asian art, she said, "Visitors need to be reminded that the art world, like the world of science, is international." She also said of her paintings, "The collection should not be thought of primarily as fine art, but rather as working tools with which a scientist endeavours to comprehend certain aspects of the world which are not science." This isn't that different to what Nelson Goodman said in his book, Languages of Art. The arts must be taken no less seriously than the sciences as modes of discovery, creation and enlargement of knowledge in the broad sense of advancement and understanding. We are still not talking about collaboration, though. We are talking about art as a way to think. We are thinking about art as a tool for scientists, not the other way around. A thunderstorm. Bubbling beakers of bright coloured liquids. Crackles of electricity, crazy hair, lab coats, white spaces, old men with beards and spectacles, the loner, the nerd, the geek, bookish and awkward, men of science, men that play God. The representation of science itself is complicated. On film, it occupies a dual space. On one side, the expert, and on the other, the antagonist. One role of exposition and another of hubris. And in the news, experts again, a calming voice or the herald of oncoming catastrophe, a cure or a curse. Equal parts thalidomide and the race to eradicate smallpox. it's easy to see why science frequently appears in art. It's fascinating. It peels back what we know and illuminates the unknown. It shows us the great void and poses questions that seem eternal. It is a tragedy and a success, a hero and a villain. It is an enigmatic smile on the canvas of humanity. Being the subject of art is different from collaboration between the two disciplines. In this case, the truth represented belongs entirely to the artist. The artist is saying, "This is how I see science." There is nothing wrong with this. However, it cannot be claimed to be in any way a collaboration. Rather, it is an observation, followed by a personal reaction. Another way in which artists do not collaborate is through recontextualizing science. Just as Duchamp placed a urinal in a gallery, artists can take scientific paraphernalia and claim it as a ready-made. We see beakers and vitrines displayed verbatim. Damien Hirst has had great success with this approach. He's even called his new studio space, located in Stroud, Science. Here, the role of the artist is as a presenter. They are not claiming to be adding to science. Rather, they are taking aspects of it as a material for their own purposes. Damien Hirst is not claiming that what happens in his studio is science. He's taking how we feel about science and transferring it to his work. He says, "I just hitched a ride on science. It's just collage, isn't it? Art is always very simple, or good art is always very simple. I took science in the way that Picasso took the bike seat and the handlebars and made the bull's head." There is a process where something more misleading can occur. This happens when an artist represents science as integral to their work without engaging in any form of collaboration. In these cases, the artist seeks to appropriate the aesthetics of science to add perceived legitimacy to their work. Let's call this practice lab coating. Typically, lab coating borrows selective ideas and imagery from scientific practices and then attempts to use them to bolster a view held by the artist via a form of pseudoscience. Often, the aesthetic borrowed by the lab coating artist belongs not to science at all, but the media representation of science. This is likely due to the fact that the true aesthetic of modern science is far closer to domesticity than it is the fantastical images of science fiction. You can view this much in the same way as claims for herbal medicines, where the language and packaging that presents it lean heavily on that of traditional pharmaceuticals to add legitimacy to a product that has none. Lab coating is perhaps less cynical than it is a fundamental misunderstanding of science and its methodologies. Most science art collaborations remain firmly within the realm of art. That is, the product is of a limited scientific interest beyond acting as an exercise in public visibility. Science needs to be replicable, reproducible, and importantly, peer-reviewed. Without these qualities, a collaboration cannot claim to be anything more than an artistic exploration. The misunderstanding stems from a failure to separate science from the representation of science. To some extent, Plato was right. Art is of little use to science, especially as a practice. Art deals in the reified and personal. Art deals with emotions and all of those human things that aren't really part of science. These emotions are useful, however, in the representation of science, and particularly scientific models. Artists are able to travel far beyond the diagrammatic and the documentational to enable people, especially the public, to engage with scientific concepts and the practice of science as a whole. The space where art and science finally meet is a fictional space. It exists, but it is imagined. It is the space of representation. A thermometer is not the temperature, but it tells us the temperature. It represents the temperature. The line of silvery metal converts something conceptual into something real and understandable. A watch is not the time, but it tells the time. It represents time. The movement of the hands or the increasing digits converts something conceptual into something real and understandable. Diagrams of processes, photographic documentation, sculptures and models of proteins. Scientists are not unartistic. They inhabit this space. However, this space is defined by artists. Through association, simile, metaphor, and context, artists are able to evoke responses and understanding of concepts they may not have encountered before. They provide us with ways to visualize and talk about things we cannot see or touch. Artists are the architects of this representational space. Sometimes we lack a representational language for a new concept. We find ourselves short of ability to articulate. The imagined space becomes unsuitable for the activity we are attempting. And this is when scientists need more space, or even a differently shaped space. And this is when they need to collaborate with artists. What was the name of the person that discovered stomach ulcers are caused not by stress, but by bacteria? They won a Nobel Prize for their work. What did Arthur Ashkin win his Nobel Prize for this year? Or Francis H. Arnold and George P. Smith? These are the famous ones. Science, as a human practice, is partially hidden. It is not clear if this is due to the removal of the human through the use of the passive voice, or the necessity for research to remain secretive, particularly in the pharmaceutical realm. Or maybe it is just the practicalities of performing science. Long hours in a laboratory, or working with statistics, closed windows with the shades drawn. Perhaps it is the fault of the scientist, being aware as they are of the observer effect. The observer effect is the theory that simply observing a situation or phenomenon necessarily changes that phenomenon. A good example is when you take the temperature of a liquid. You use a thermometer. You place it in the liquid. The silvery liquid rises or falls, showing you the temperature. It is, however, also altering the temperature of the liquid which you are measuring. If you observe a scientist, perhaps they change too. Maybe they become something other than a scientist, a performer, for instance. And if that is the case, you are no longer observing a scientist, you are observing a performer. Performers are generally okay with being observed. We were there to observe the scientists, mostly. But first, let's talk about the environment. Not the environment at large, not the one we should be really worried about, the one full of plastic and problems. Let's talk about the very specific and particular one, located at 51 degrees, 52 minutes, 40.274 seconds north, and 0 degrees, 24 minutes, 37.591 seconds west, 3 floors up. This is the part of the Luton campus of the University of Bedfordshire that has been designated as the Institute of Biomedical and Environmental Science and Technology, or by the slightly catchier acronym of iBEST. Sets of double doors demark the space at the 3 ends of a branching corridor. Initially, there is no apparent difference between the corridor outside iBEST and the corridor within. The border of this space is conceptual. This was once a generic space. An architect designed it as a set of rooms joined by a section of corridor, much like the other rooms on the campus, and much like the other corridors. There is no special architecture that makes this space particular or distinct. The architecture of science is almost identical to the architecture of media arts. However, the scientists have occupied this space. The first sign of this occupation are the doors, or rather, the adornments on them. Elsewhere in the building, a door may display the name of the room, or perhaps the expected occupant. But here, every door is instructional. They are labelled and illustrated. The contents of the room is listed: compressed gas, substances hazardous to health. The text is reinforced with a variety of diagrams that depict dead fish and explosions. Each door becomes a portent of possibilities, of potential. Portals of potential. It is with some relief that we never saw this potential realised. The next indicator that scientists inhabit this space is more ambiguous. It is likely that it existed before they moved into the space and acted more as a signpost that this space was intended for science rather than as a result of their occupancy. Imagine the artwork that lines the walls of the corridor. Are there beakers full of exciting coloured liquids? Perhaps an assortment of strange-shaped pills? Is that a picture of a microscope? This space has been lab-coated. We spend some time pondering on why you would choose to show a picture of a microscope rather than the wonderful things that you can actually see with a microscope. Later, when we finally meet a scientist, they show us some of their work. They hand over photographs that they have taken using a microscope in the space adjacent to the picture of the microscope. The images show small amounts of coloured microplastics inside single-celled organisms. They are meaningful and aesthetically attractive. The scientist is asked if they think it would be better to have their pictures on the wall. They seem uncertain of the question being asked. We were unable to determine who chose to decorate the walls. We can only guess at their level of scientific expertise and their involvement in creating the images in the first place. Beyond those walls and through the doors, the practicalities of science take over, particularly the practicalities of teaching it. The laboratories consist mostly of multiple occupancy benches sporadically interrupted by lumps of machinery. Sometimes this configuration seems at odds with the space. Ghosts of alternate doorways are covered with cabinets or refrigerators. This is a space that has been moulded by the activities that occur within it, rather than being designed for them in the first place. There are other examples of this. There is a room that is used solely for the storage of chemicals. It is a small room containing several sections of steel cabinets and securely locked cupboards. There is little room to move between the shelves and only just enough to navigate the central aisle with a trolley. What is most striking about this room is the lack of light. Light is a problem for storing chemicals. Many of them interact with light or the heat it inevitably causes. One entire wall of this room consists of glass windows. They have been modified using tinfoil to block out the light. A similar situation happens in another room. This room has adequate ventilation for office workers, admin staff, or perhaps even as a small seminar room. What it doesn't have is adequate ventilation for the solvent-based chromatography that is conducted within it. This room does not have windows. Instead, a domestic air conditioning unit has been installed. It doubles up as a doorstop, keeping the door open. This environment is an adopted environment. It is occupied but not designed. It is a real space with real boundaries. The problems this creates are familiar to us. The problems of this physical space are exactly the same as the problems of the fictional space of representation. There is the misrepresentation of science through lab coating, a representation of science through a mediated lens of fiction, constraints born not of science, but of another discipline, in this case, architecture. The modern representation of science in the media is particularly masculine. The tropes tend to condense around four main themes: the scientist playing God, the scientist as lone explorer, men in white coats, the mad scientist. This essentially Victorian view of the people involved in science seems to be reinforced by a cycle of portrayal in fiction being related to the representation of science in real life. Think about the term Frankenstein foods for a moment. Here, a male character from a novel written in 1818 is attached to the modern process of genetic manipulation. The term Frankenstein foods is clearly used to promote a negative view of the process. By linking the story of a monster and the loss of its control by its creator, the usage of this term is an attempt to add a fictionalized narrative of horror to make a point. Here, representation is deliberately distorted. There is a side effect of this too. Dr. Frankenstein was an individual. Dr. Frankenstein was a man. In reality, most modern scientific endeavours are the efforts of teams. Furthermore, many of the individuals within these teams are women. This is just one way in which women are silently edited from the representation of science. When we talk of mad scientists, we think of men with crazy hair. There is a lack of representation of women even within this negative fictional view. There are examples, however, with the most interesting being the case of the first mad scientist in modern literature. The 18th century English poet Christopher Smart wrote a piece called The Temple of Dullness in 1745. It featured a character, a woman named Mathesis. Next to her, mad Mathesis, her feet all bare, and girt, untrimmed, with loose neglected hair. No foreign object can hear her thoughts disjoint. Reclined she sits, and ponders o'er a point. Before her, lo, inscribed upon the ground, strange diagrams the astonished sight confound, right lines and curves with figures square and round. With these the monster, arrogant and vain, boasts that she can all mysteries explain, and treats the sacred sisters with disdain. She, when great Newton sought his kindred skies, sprung high in air, and strove with him to rise, in vain. The mathematic mob restrains her flight, indignant, and on earth detains. Ere since the captive wretch her brain employs, on trifling trinkets and on gewgaw toys. Mathesis is Greek for science. Mad mathesis, mad science. Of course, here, mathesis seems to be a proxy for science itself, the thing that drives men like Newton, a malevolent muse, if you will. It's not immediately obvious why women fail to occupy the role of scientist within literature, or the media at large. It is not just a question of female representation as a whole. There are examples of women portraying pirates, detectives, and cowboys, and this seems to also undermine the position that the roles in literature are proportional to the roles that women inhabited at the time. It seems unlikely that there were more female pirates than female scientists. There have been no shortage of influential scientists who happen to be women. Only 40 years after Christopher Smart wrote The Temple of Dullness, the British Astronomer Royal Dr. Neville Maskelyne wrote to the 38-year-old Caroline Herschel, congratulating her on the discovery of a series of comets. Sometime later, she would be awarded with an honorary fellowship of the Astronomical Society. Margaret Cavendish had been prolific and well known for over 100 years before Herschel spotted her first comet. A philosopher, writer, and scientist, she published under her own name, and her work addressed gender, power, manners, scientific method, and philosophy. In 1666, Cavendish also wrote and published one of the earliest examples of what would eventually become known as science fiction. The Blazing World was a utopian romance. Sadly, the story does not feature a female scientist. Margaret Cavendish was also the first woman to be invited to the Royal Society. It is worth noting, however, that the Society only admitted its first female members, crystallographer Kathleen Lonsdale and biochemist Marjorie Stevenson, in 1945. Herschel and Cavendish were exceptional scientists, but being women does not make them exceptional as scientists. Marie Curie, pioneering research into radioactivity. Ada Lovelace, mathematician and first computer programmer. Lise Meitner, led the group who first discovered nuclear fission of uranium. Rosalind Franklin, X-ray crystallographer who contributed to the discovery of the structure of DNA. Dorothy Hodgkin, chemist who developed protein crystallography. Jocelyn Bell Burnell, astrophysicist who co-discovered the first radio pulsars. Diane Fossey, pioneering primatologist. Rachel Carson, marine biologist and author credited with advancing the environmental movement. Vera Rubin, astronomer who pioneered work on galaxy rotation rates. Grace Hopper, pioneer of computer programming who invented one of the first compiler-related tools. Mary Anning, paleontologist and discoverer of the ichthyosaur and the pterosaur. Sophie Germain, mathematician, physicist and philosopher working in number theory. Sally Ride, astronaut, physicist and engineer, the youngest American astronaut to have travelled to space. Linda B. Buck, biologist and geneticist working with olfactory sensors. Lynn Margulis, evolutionary theorist and biologist, science author, educator and popularizer. Virginia Apgar, obstetrical anesthesiologist, inventor of the Apgar score to assess the health of newborn babies. This is not an exhaustive list. The hidden scientist is also a form of misrepresentation. The underrepresentation of women seems intentional. Seeing science as the domain of men, whether they are brave explorers of new frontiers or simply playing God, is a deliberate act of self-delusion. This is not because they are women, but rather because their presence as women needs to be hidden. It is almost as if there is an attempt to conceal an awkward fact, something intrinsically linked with the presence of women or our perception of them. There is something familiar about a laboratory, especially when you get past the warning stickers. There's a fridge in the corner. It looks like the one you have in your kitchen. It is made by the same company. There are cupboards too, countertop work surfaces with fitted sinks. There is a microwave, 800 watts. It even has a setting on the front for baked potatoes. A serving trolley stands next to something that looks suspiciously like a pressure cooker. Knives, forks, spatulas, measuring vessels. The language you hear talks of plates and dishes. There is kitchen roll on the counter. Tinfoil too. Not specialist super science tinfoil, just tinfoil from Tesco. Lists of instructions or recipes tell you the amounts that you then weigh on scales. There are cleaning products, normal, everyday cleaning products. If this is science, which we have been told it is, then your mum is a scientist. Irene MANTON used photography a great deal in her research. She took pictures of the things she observed through the microscope. She worked much like an artist, producing numerous prints before selecting one that she thought was particularly right. Irene would give the same advice to students too. Photograph and print before you look and examine afterwards, making the practice an essentially reflective exercise. These were the images, photographs of chromosomes, cilia and Golgi vesicles that hung on her walls next to a work by Picasso. She appreciated them for their aesthetic qualities as much as their informational ones. Photography, as a practice, exists as a perfect example of a collaboration between science and art. Its physicality is one of chemistry, physics and engineering, the light-sensitive film, the way that light interacts, a shutter open for a fraction of a second. Its expression, however, becomes one of artistic intent, choosing the subject and how to represent it, choosing a subject and what it represents. If we say that this collaborative space of representation is used by science and defined by art, then the camera is a perfect model of this world. The photographs don't just tell us about the thing being photographed, but about the person doing the photographing. Irene Manton was also the subject of a photograph. It was 1975, 6 years after she retired. It was International Women's Year. Vogue magazine celebrated the event with an article on eminent professional women. Irene was, of course, included in this. Accompanying the article was a photograph of her. The stools are not for sitting on. The stools are for perching. Sitting is a bad idea. There is a chance that you will drop something. Maybe it will be hot, or maybe it will be a room temperature liquid that will eat through you as if you were made of foam. If you are sitting, you end up with this in your lap. If you are perching, there is a chance that it will run down your lab coat. This is one way that the practice of science influences the movements of the people that are involved in it. There are some movements that you can read. An Erlenmeyer flask is used in the chemical process of titration. Chemists have a particular way of holding the flask so that they can add liquid from the burette and swirl it in the flask at the same time. In microbiology, the flask is often used in the preparation of microbial cultures. In this case, it is important that the top is covered, usually with a stopper. A biologist will often swirl the flask with their palm against the stopper as an extra precaution. These movements tend to become habits. You can read whether a scientist initially trained as a chemist or a biologist. Other movements are taught and practiced. The donning and removal of gloves as part of the practice of aseptic technique. This ensures an experiment is not contaminated, and that an experimenter is not exposed. There are tiny printed instructions on some packets of gloves that look like dancing patterns. Don't touch your face. Some taps you operate with your elbows. There are machines throughout the space that replicate human movements and perform them repeatedly. There are machines for mixing. There are machines for separating, stirring, shaking. These machines do things quickly and efficiently. Then there are machines that add tiny, specified amounts of fluid into little plastic receptacles, and they perform this action precisely, over and over. These machines are not necessarily faster. They are there to do an action without human supervision, much like a dishwasher. The dishwasher is in the next room. Experimental photography and photographic experiment share a similar space. IRENE MANTON worked in this space, pushing at the boundaries and making it larger, making it fit her needs. The original architect of this space was the nephew of the first woman to be awarded a gold medal of the Royal Astronomical Society, Caroline Herschel. John Herschel was also fascinated by astronomy. He would go on to serve as president of the Royal Astronomical Society 3 times. However, it can be argued that his greatest contributions to science came from his involvement in photography. He invented the process of the cyanotype, a way of capturing images that rendered them as white on a cyan blue background. The process could also be used to provide low-cost, accurate copies of images, and as such, they would later find use as blueprints, the standard way of displaying 3-dimensional spaces on a 2-dimensional plane for architects and engineers. He also discovered a way to fix images, to preserve them once they had been developed. You can still see one of his first photographs. It is a glass plate dated 9th September 1839, and it shows a 40-foot telescope pointing towards space. 1839 also happened to be the year when Herschel coined the term photography, and quickly followed it up with the application of the terms negative and positive. These words, as mundane as they are now, created the basis for a new science and a new form of art. John Herschel was not just a scientist, nor just an artist, or just a photographer. He was all of these, and he was an architect of the shared representational space between science and art. The radio is on. The radio is almost always on. It can't leave. It is contaminated. The radio is a prisoner of this space, an interloper of art. The dial reads 97-ish. It could be Heart FM. Whitney Houston is in the laboratory with us. She wants to dance with somebody. Whitney Houston is not a prisoner of this space. She is transient, but present. She could be in 1,000 laboratories. We have to consider if she will be present for some great discovery. The University of Bedfordshire is currently building a new £40 million structure at its Luton campus. The building will be devoted to teaching and research in science, technology, engineering and mathematics, subjects that are commonly referred to as STEM subjects. The STEM building will spread 6,000 square metres of teaching and laboratory space over 4 floors. It will comprise of 70 miles of power cable and 350 miles of data cable, enclosed in 5,500 tonnes of concrete. Reports suggest that it will contain enough sheets of plasterboard to cover 3 football pitches. A football pitch is not an SI unit. Bill Rammell, Vice-Chancellor of the university, says, "Our new STEM building will support the ambitions of regional policymakers to enhance the skills base in Luton, extending opportunity for local residents and attracting investment to the region." Colin Moses, Director at MCW Architects, adds, "This flexible building will enable the university to increase its undergraduate community, pursuing a wide range of science and technology-focused activities in a collaborative and stimulating environment that is specifically designed to facilitate the latest patterns of teaching, learning and research." The new building also provides a platform of outreach and inclusion with a highly visible and accessible ground floor space that can be used for group-based learning activities and as a shop window for the university. The new laboratory spaces seem well designed. They feature adjustable lighting and ventilation. There is no official record of what sort of artwork will adorn the walls. Perhaps in the spirit of IRENE MANTON, they will display images of the scientists' work alongside artwork that they like, creating a dialogue across the walls of the space, linking the physical space of the building with the imaginary one of representation. Empiricism is the philosophical theory that all knowledge is based on experience derived from the senses. As a fundamental part of the scientific method, it means that all hypotheses and theories must be tested against observations of the natural world rather than resting on a priori reasoning or induction. Modern biochemistry, as we observed, is Tom taking one clear, colourless liquid and mixing it with a second, different, clear, colourless liquid in a beaker with some masking tape stuck to the side, to the sound of Whitney Houston on the radio. He stood up at a bench. There are bottles wrapped in tinfoil and an onion. Across the room, one of his female colleagues, Ciara, is working on something similar in coordination with another female researcher, Gregory. Tom swirls the flask, holding it at the top, much like a chemist would. He creates a third, unique, clear, colourless liquid in order to show us how it is done.